discuss some question of linear algebra as a basic concept. This question actually very important for higher study, but this question depends on just basic knowledge. At first, I will say one question which had come CSIR NET June 2021 exam. The question is, consider two statements given below. Option 1. There exists a matrix N belongs to M4 cross 4 matrix with real field such that the vector contains 1, 1, 1 minus 1 and 1 minus 1, 1 is a basis of row space of this matrix N, and the vector 1, 2, 1, 4 contain the null space of this matrix N. Notice these two vectors are linearly independent. So, these vectors be the basis of row space of this matrix and null space of this matrix. Here given only one vector. There exists also another vector because here the dimension of the matrix is, this is the 4 cross 4 matrix, dimension of this vector space would be 4. So, at first say the option 1, then I will see option 2. Just first say what has told option 2. Option 2 has told there exists a matrix M belongs to M4 cross 4 matrix whose entries are real field such that the vector 1 1 1 0 transpose comma 1 0 1 1 transpose is a basis of column space and the vector 1 1 1 transpose comma 1 0 1 0 transpose be the member of null space of this matrix, then which of the following statement is true? Option 1. Statement 1 is false and statement 2 is true. Option 2. Statement 1 is true and statement 2 is false. Option 3. Both statement 1 and 2 are false. Option 4. Both statement 1 and 2 are true. Are you getting this option? Well, now let's see option 1. Since in the matrix these vectors are basis of this row space, so obviously these two vectors are linearly independent and span row space. That means row spaces would be generated by these two vectors. And since this vector 1 2 1 4 be the member of null space, that means this vector contain here, we all of us know null space is the perpendicular complement of row space. So obviously these vector here given in the question in null space contain this vector. That means this vector dotted with these two vector obviously would be 0. That means 1 2 1 4 dotted with 1 1 1 minus 1. Obviously this dotted would be 0 because null space is the orthogonal complement of row space. So this is equal to, this would be 1 plus 2 plus 1 minus 4. Notice obviously this value equal to 0. And also 1 2 1 4 dotted with 1 minus 1 1 1 would be this value equal to 1 minus 2 plus 1 plus 4 Notice here this value equal to 4. That means this is not equal to 0. So obviously, since null space is the orthogonal complement of row space, that means this vector 1, 2, 1, 4 does not contain in null space, because here this is not equal to 0. So obviously statement 1 is a false statement. Now I will see if statement 2 is true or false. Here notice these two vector is a basis of column space, and here has indicate these two vector are member of null space. And notice, since these two vector are linearly independent. Why linearly independent? Because these two vector is not combination of others. So obviously these two vector are linearly independent. So these two vector be the basis of this matrix null space. Here the matrix N is generated by these two vectors which are linearly independent. So this is the basis of this matrix, and obviously here the matrix also contain other two vector, but since here two vector which is linearly independent, also null space contain two vector which is also linearly independent. So by rank nullity theorem we can tell these two vector would be obviously linearly dependent. That means these two vector would be combination of these two vector. So consider this vector as a alpha and this vector as a beta. Then this vector would be alpha plus beta, alpha, here also alpha plus beta, and here beta. For this column, consider this is A and B. Then this would be A plus B, A plus B and B. Since these vector dotted with this vector be the 0, so obviously this matrix dotted with this vector. For calculation, simple calculation, at first I will use this vector, then this matrix dotted with this vector would be 0. Therefore 1 plus 1 plus alpha plus beta plus A plus B equal to 0, and here would be 1 plus alpha plus A equal to 0. This line dotted with this is the 0, then this would be 1 plus alpha plus beta plus A plus beta equal to 0. And here 1 plus beta plus B equal to 0 vector, and from this expression alpha plus A equal to minus 1, beta plus B equal to minus 1, just put the value, then I will get alpha equal to minus 1, beta equal to 0 and A equal to 0 and equal to minus 1. Now obviously this matrix would be such type, since alpha equal to minus 1 and beta equal to 0, that means this value would be minus 1, value of alpha would be minus 1, alpha plus beta here also would be minus 1, beta equal to 0. Since A equal to 0 and B equal to minus 1, so this 1, here 0, here minus 1, here also minus 1. So obviously there exists such type of matrix whose row space would be generated by these two vectors, and if you consider this vector also as a null space, obviously you will get another value of alpha, beta and AB. So 1 is a right option. Statement 1 is a false and statement 2 is a true. Option 2, 1 is a true and statement 2 is a false. This is also wrong option. And option 3 indicate both statement 1 and 2 are false. This is also wrong. And option 4 indicate both statement 1 and statement 2 are false. This is also wrong option. That means only option 1 is a right option. there exists a matrix whose row space is generated by this vector and null space is generated by this vector. But option 1 is a wrong option because there does not exist such type of matrix whose row space is generated by this vector and null space is generated by this vector. Now I will see another question which had come 2021 IIT JAM exam. The question is, consider VB a finite dimensional vector space and consider a linear transformation T from vector space to itself and consider RT denote the range space of the T and nullity T denoted the null space of this vector space such that V belongs to this vector space such that TV equal to 0 of the linear transformation T. And if rank of T equal to rank of T square, then which of the following statement is an unnecessarily true? Option 1, nullity of T equal to nullity of T square. Option 2, rank of T equal to rank of T square. Option 3, nullity T intersection rank of T equal to singleton set 0. And option 4, nullity T equal to singleton set 0. This is very basic question. For review, just see here T be a linear transformation from vector space to itself and given rank T equal to rank T square. We have to show nullity T equal to nullity T square for option 1. If X belongs to null space of the T linear transformation, then that implies obviously Tx equal to 0 vector. We all of us know. Also, T times Tx equal to T square X equal to 0 vector. This means and T square X equal to 0 means obviously X belongs to null space of this linear transformation T square. That means X belongs to null space of T imply X belongs to null space of linear transformation. That means null space of this linear transformation contain null space of this linear transformation T square. So, since given rank T equal to rank T square, that means by rank nullity theorem, we can tell, and since T be a linear transformation from vector space to itself, so dimension of V equal to rank T plus nullity T. Since rank T equal to rank T square, obviously T square be a linear transformation from vector space to itself, then obviously dimension of V equal to rank T square plus nullity T square. Then just equate these two equation. Then rank T plus nullity T equal to rank T square plus nullity T square. And since rank T equal to rank T square, that means that imply nullity T equal to nullity T square. Here I have got null space of this linear transformation contain null space of this linear transformation T square. And also I have got nullity T is same as nullity T square. That means since this contain in this transformation and since nullity T equal to nullity T square, we all of us know nullity T means dimension of null space. Since both this equal and this contain this, so obviously null space of this linear transformation is equal to null space of the linear transformation T square. So obviously option 1 is the right option. Option 2 imply rank T equal to rank T square. Is it option 2? Similar to before, X belongs to range space of the linear transformation T square means obviously this means T square Y equal to X where for some y belongs to the vector space V. And t square y means t times t of y equal to x. This is obviously, if y belongs to the vector space V, then there exists a linear transformation T from vector space to itself such that T of y belongs to V. And this means actually T of y equal to Z. Now, since T of y equal to Z, so put the value here. So there exists Z belongs to vector space V such that this would be, just put the value here, Tz equal to x, and Tz equal to x means obviously x belongs to range space of T. So here I have considered x belongs to range space of T square, and I have got x belongs to range space of T. That means range space of T square contain range space of T square. Range space of T. Okay. But in the question has given rank of T always equal rank of T square. And I have got range space of the linear transformation T square contain the range space of the linear transformation T. That means I have got two space whose dimension are same, and these two space contain one another space. Rank T square contain rank T. That means obviously range space of the linear transformation T is equal to range space of the linear transformation T square. Okay. That means option 2 is the right option. I will say nullity T intersection range T equal to only singleton set 0. Consider an arbitrary vector x who is contain null space of this linear transformation T intersection range space of this linear transformation. And x belongs to null space of this linear transformation is imply Tx equal to 0. And x belongs to null space of the linear transformation T means Ty equal to x, where for some y belongs to the vector space V. And now apply T on both sides. Then obviously T square y equal to Tx, and since Tx equal to 0, just put the value here would be 0. That means that imply from this expression, since T square y equal to 0, that means y belongs to null space of this linear transformation T square. Also given, I have got null space of the linear transformation T is equal to null space of this linear transformation T square. So, since y belongs to null space of this linear transformation T square, this is obviously equal to null space of linear transformation T. That means from this expression, that imply y also belongs to null space of this linear transformation T. So, obviously, T of y, who is actually equal to x, this value would be 0. That means I have considered one arbitrary vector x who is contain null space of this linear transformation intersection range space of this linear transformation. But I have got this vector is nothing but only 0. So obviously null space of this linear transformation T intersection range space of this linear transformation T equal to singleton set 0. That, and option 3 is a right option. Now fourth option imply if rank of T equal to rank of T square, then nullity of T only contains 0 vector. For this, consider a linear transformation T from R2 to R2 such that T of xy equal to 0, y. Now apply T on both sides. Then t square xy would be t of 0 comma y, and by definition t of 0 comma y equal to 0 comma y. That means t square equal to t. So obviously rank t square would be rank t. That means I can consider this example. Then nullity of this linear transformation is xy such that t of xy equal to 0 0, and t of xy means obviously 0 y equal to 0 0 vector, and this means actually set up those elements x comma 0 such that x belongs to V. Therefore, here I have got one linear transformation which has satisfied all condition rank, because here rank, the condition is rank t square equal to rank t, but their null space not equal to singleton set 0. So option 4 is a wrong option. That means if rank t equal to rank t square, then their null space always would be same. Means null space of t equal to null space of t square. Also their range space of equal to. That means range space of this linear transformation is equal to range space of t square, and intersection of these two space only contains singleton set 0. But null space of this linear transformation can be any number, not only 0. Okay? And this is just basic question. This depends on just basic concept. Today I will stop here. In my next video, I will discuss another type of question. Actually, linear algebra is very important for higher study. So, I am discussing this topic elaborately. Okay? See you soon. Thank you so much.